Hello and welcome to this lesson on quantum computing. We're going to take a look at some of the basic principles behind it and get a feel for the kinds of areas that it could make a huge impact in both computing and human society in general. Okay, and there's a fantastic picture of a quantum computer as they are currently being built and prototyped right now. Fairly impressive looking device. And as usual, we start our lessons with our normal numeracy and literacy tasks. So have a go at those ones. Okay, so needless to say, quantum computing is extremely complicated. You know, there are people out there that have done PhD after PhD in this area, and we're still discovering more and more things. And quantum mechanics, that sort of field, or that branch of physics that looks at the extreme, at the quantum level, the extremely small, smaller than atoms. This is the level on which we're operating. It's difficult to get your head around sometimes because the laws of normal physics, the physics that we deal with every single day, you kick a ball, it goes up, it comes down, you press a button, something happens. Like, the basic rules of physics don't tend to apply when you get down to the quantum level, which can be quite a mind-bending process to sort of think about. So when it comes to some of this, you have to kind of suspend your idea of what's normal and what isn't normal. So let's have a quick look then. So one of the problems that normal computing has is that it relies on this transistor technology, and it's done very, very well out of this transistor technology. Something called Moore's law has meant that computing power has basically doubled every couple of years for decades now, and that's more or less held true as our technology has got better. And basically, the key to that is making these transistors smaller and smaller and smaller. These transistors control computer bits, which are the ones and zeros behind computer code. The better that we can do that, the better we can do our calculations. The second bit, or where this process comes into trouble, is when it gets so small, something called quantum tunneling takes place. Now, that's on a quantum level. Electrons, which is what we usually use for our computer bits, they start to go a bit crazy. They can reappear on the other side of logic gates. Like I said, this is quantum mechanics. It doesn't make much sense. How can something suddenly just vanish and then reappear somewhere else? Well, on a quantum level, they do, and that causes great problems for traditional computing going forward. But it does offer an opportunity for quantum computing. Quantum computing uses not bits, but something we call qubits. And this is the really clever bit about them. They are not just ones and zeros. They can be both at the same time. Not only can they be both at the same time, but they can actually be a value in between the 1 and the 0 at the same time. And they can hold all values between 1 and 0 simultaneously. That means something quite extraordinary. That means that rather than if you want to crack a password, for example, you don't have to run a million different variations of what the password could be, one after the other. You can run a million computations simultaneously by using a qubit. The sheer magic of not knowing what it is means that you can actually use it to be anything and everything. And so that is just the magic behind quantum computing. So here's another sort of diagram that shows that. A classical bit is a 0 or a 1. A qubit can be both. And that is the power that this offers. Right. It takes a bit of getting used to this. And so there are 3 videos here that you can access. There's a bronze, silver, and gold level video. I would thoroughly recommend trying to watch and answer the questions on all 3. The first time you watch the video, there might be some things there that don't make sense. The second video you watch, things start to make a bit more sense, and by the third, you're starting to put things together again. So I'd recommend watching all 3 if possible. So have a quick read through those, pause this video, have a quick watch through those 3 videos, and then move on to this slide here. You'd have heard in those videos, they mentioned something called exponential. It doesn't mean very much on face value. Exponential. So what? What does that mean? Well, the power of exponentials are mind-boggling. Okay, take a look at this, for example. If you have a classical computer using classical bits, and you've got 100 bits, you can hold 200 different values. If you've got 100 qubits, because the way these are calculated is in an exponential way, you can actually hold the value of that many bits. And I don't even pretend to know what that number is. I simply cannot count that high. It is an extraordinary number. But that gives you an idea of the power of quantum computing. You can perform that many calculations simultaneously, potentially. This is not just computers that are a bit faster. This is next level stuff. This puts computing into a completely different realm. And so we need to start thinking then, therefore, what could this technology be used for? Now, you'd have heard in one of the videos, the scientist said that it won't be used in our traditional computers. It won't be used in your mobile phone. It won't be used on your laptop. It's not going to be used so you can watch Netflix. Okay, we already have the technology to do that, and quantum computing can't really assist. But in certain areas, quantum computing is a clear, distinct advantage. So have a quick read through this article here and try and attempt to answer some of these questions, okay, by filling out this grid here. Okay, there's a copy of this in the resources section of the PowerPoint. Now, this is probably the best explanation I've found of thinking about quantum computing. So if someone says to you, what is quantum computing? And you have to explain it, this is probably the quickest way of doing it. This is an example here mentioned at the Wired 2014 conference, and it goes something like this, okay? If you were given the task of finding an X written on a page of a book among the 50 million books in the Library of Congress, you'd probably never find the X, okay? Well, you wouldn't. In a lifetime, you couldn't check all 50 million copies of the book, and you'd never find it. But if you were able, through some magical means, to split yourself into 50 million copies of yourself, and then simultaneously check all 50 million books, well, you'd find the X. You probably often thought this yourself, sometimes I just wish there was two of me. One of me could be asleep whilst the other one was doing the homework, whilst the other one was out playing, whilst another one was, learning a new language. How fantastic would that be? I'd be 4 times more effective. Okay, well, that's basically what quantum computing allows you to do. A quantum computer splits you into 50 million versions of yourself to make the work quick and easy. So have a quick look through these 5 areas in which it could be drastically important. And check your answers against this grid here. Okay, I'm not going to go through them because they were written down for us there, but they're incredibly interesting. And as an extension task, try and label these things 1 to 5, in which area you think would be the most important. I will very quickly just talk about artificial intelligence and its potential applications there. Okay, most AI, as we know, is something called machine learning, right? So let's take DeepMind as an example. They are a company in Britain that created a computer that could beat the world Go champion. Now, Go is like a Chinese version of chess, if you want. That's chess is, it's more complicated than chess. By a factor of, some margin, it's much more complicated than chess. And lots of people said that they couldn't create a computer that could beat the world Go champion. And they did. And they did it very, very quickly. And the way they did it was through machine learning. Basically, they created a computer that could play Go, and then they let that computer play millions of different versions or millions of different games. And it remembered how each game went. So then when it came to playing the real Go master, it could anticipate and predict what was going to happen next and then make a move to try and win the game. That's basically how machine learning works. You trial and error. You do a process again, you learn by your mistakes. You do it again, you're a bit better, you make another mistake, you learn from it. The next time, you sort of fine tune your process over millions of different variations. And that's basically how AI works. It's not about creating a sort of copy of the human brain. It's about creating an algorithm that has basically tried and tested every possible method, and so it can, it knows what it's doing based on past experience. With quantum computing, well, you're going to be able to teach these machine learning AI algorithms so much faster than we can currently, and in tasks and in processes that are far more complicated than simply the winning the game Go. So, for example, if we wanted to find out how traffic systems work, to take in that last example there, we could just run all the multiple possibilities. So, for example, air traffic control. What's the best way of moving people around the planet on aeroplanes? Well, you can just use quantum computing to get an AI to just trial every possible flight path in existence before it can settle on the best, most efficient combination possible. So, truly incredible stuff is on offer here, okay? And there is a quantum computing close activity for you to have a go at here, okay? Right. Hope you found that useful. Have a quick go at the quiz that can be found at wolseyacademy.com/ICT future. Okay, hope that helps.